for projects. In this video, we are going to explain about the project, which is efficacy of CNN bidirectional LSTM hybrid model for network-based anomaly detection. Introduction of the project. Over time, the transmission of information has transitioned across wired, wireless, and guided networks. This evolution, driven by advancements in network technology, now plays a pivotal role in shaping the routines of individuals in their daily activities. The bedrock of a secure system lies in upholding the principles of confidentiality, integrity, and availability. Successful implementation of these principles ensures information security by preventing unauthorized access, use, disclosure, modification, recording, or destruction of the data. While firewalls and antivirus software are standard tools for network protection, their limitations become apparent. This project contends that these conventional defenses fall short, particularly in detecting outliers and anomalies not covered by predefined rules. Delving into the realm of intrusion detection, two main methods surface, which are signature based system and anomaly based systems. The focus shifts to anomaly detection, exploring both network based and host based intrusion detection systems and addressing the challenges like false results arising from shifts in user behavior. Traditional machine learning algorithms face challenges in handling large datasets, prompting a shift towards deep learning methods. The projects focus on the development and evaluation of an CNN by LSTM model for intrusion detection in network traffic data. Objective of the project. The primary goal is to address the limitations of the existing network anomaly detection systems. This involves a focused effort on selecting optimal hyperparameters, refining the training and testing procedures, and optimizing the architecture of deep neural network. The aim is to enhance the overall performance of anomaly detection systems. The project seeks to experiment with intrusion detection models using two specific datasets, which are NSL-KDD and UNSW-NB15. The key objective is to improve the accuracy of these models, particularly in identifying instances of network intrusion or anomalies. The project aims to design and implement a specialized model known as convolutional neural network with bidirectional long short-term memory. This model is specifically tailored for intrusion detection in network traffic data. CNN layers are effective in capturing local features, while BLSTM layers address the challenges of retaining long range information in sequential data, contributing to more accurate predictions in intrusion detection. The chosen architecture involves the strategic use of convolutional layers and pooling layers for feature extraction. These layers are adept at capturing spatial hierarchies and local patterns in the data. Additionally, a fully connected dense layer is employed for classification, focusing on global patterns and decision making. This combination aims to enhance the model's ability to recognize both local and global features relevant to intrusion detection. The project involves a comprehensive evaluation of CNN BLSTM model detection accuracy by systematically tuning key hyperparameters such as optimizers, learning rate, epochs, batch size, and dropout rate. The project aims to identify the optimal configuration for the model. This comparative analysis is conducted on two distinct datasets to ensure the model effectiveness across diverse different scenarios and types of network traffic. To implement this project, we need software and hardware requirements. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. To implement the project, we have designed various steps in the flow of work. The first step is importing the packages. In this initial step, the necessary Python packages and libraries are imported into the project. We imported NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for data visualization, Scikit-learn for machine learning, Keras for building neural networks, Flask for web development, and SQLite for database interactions. The next step is exploring the dataset. Here we understand the structure and the content of NSL-KDD dataset and UNSW-NB15 dataset, which is commonly used in intrusion detection research. We load the NSL-KDD and UNSW-NB15 dataset, examine its features, and get an overview of the data distribution. The next step is data processing. Here, we convert the dataset, which is raw dataset, into Pandas data frame for easier manipulation and analysis. We use Pandas functions to create a structured data frame from the raw dataset. We prepare the data for training using Keras by transforming it into a format that is compatible with neural networks. We utilize Keras functions to pre-process the data. We remove unnecessary or redundant columns that do not contribute to the modeling process. We use pandas to drop the columns that are not relevant for analysis or modeling. We transform binary classes to a format suitable for modeling and adjusting binary classes, ensuring compatibility with the chosen modeling approach. The next step is visualization using Seaborn and Matplotlib. Visualizations are created to gain insights into the data distribution and relationships between variables. Seaborn and Matplotlib are the functions that are used to generate plots, histograms, or other visualizations that aid in understanding the dataset. The next step is label encoding using label encoder. Categorical labels are converted into numerical format, allowing machine learning models to process them. Label encoder is utilized from scikit-learn to encode categorical labels. The next step is feature selection. In this step, we select relevant features that contribute the most to the modeling process. We used select percentile from the scikit-learn to choose the top features based on statistical measures. The next step is splitting the data into train and test. In this step, we prepare the data for training and testing by splitting the data into training and testing sets. We use scikit-learn to perform a train test split. Building the model. Here we define the architecture of the machine learning and deep learning models. We use Keras for deep learning, scikit-learn for machine learning, and we create the structure of the model specifying the layers, neurons, and activation functions. The next step is training the model. Here we train the model using prepared training dataset. The next step is Flask framework with SQLite for sign up and sign in. We implement user authentication functionalities using Flask and store user information in an SQLite database. We set up routes for user registration and authentication using Flask and use SQLite to manage user credentials. The next step is user gives input as feature values. Users are allowed to input feature values for prediction. The given input is pre-processed for prediction. User input is prepared for prediction by applying the same pre-processing steps used during the training. Previously defined data processing steps are used to pre-process the user input. Training the deep learning model is utilized for making the predictions. Final prediction outcome is presented to the user through the front end of the application. Algorithms which are used in the project are CNN, which is convolutional neural network. It is a deep learning architecture specialized in image processing, featuring convolutional layers for feature extraction and pooling layers for downsampling. CNNs are effective in image and pattern recognition tasks, making them suitable for extracting features from the network traffic data. The next one is CNN with BiLSTM with NADM. It is a hybrid model combining convolutional neural network and BiLSTM layers. BiLSTM is a type of recurrent neural network architecture that extends the capabilities of traditional LSTMs by processing sequences of the data in both forward and backward directions. They are particularly effective in handling sequential data. Coming to NADM, which is Nestrov Accelerated Adaptive Movement Estimation, it is an extension of ADAM optimization algorithm. It combines the advantages of Nestrov Accelerated Gradient and Adaptive Movement Estimation. NAG helps in accelerating the convergence of anticipating future gradients, and ADAM adapts learning rates individually for each parameter. NADM is chosen for its ability to handle sparse gradients and noisy data, which can be prevalent in network traffic datasets. This combination of CNN and BiLSTM allows the model to capture both spatial and temporal dependencies in the data. The next one is CNN with BiLSTM with ADAM. Similar to NADM configuration, this model combines CNN and BiLSTM layers with the ADAM, which is adaptive moment estimation. It is an optimization algorithm that computes adaptive learning rates for each parameter by considering both the first order momentum and the second order momentum of the gradients. The combination with the CNN and bidirectional LSTM leverages the strengths of each layer to capture complex features and sequences. Next one is CNN with BiLSTM with RMS prop. It is another variant of hybrid model utilizing RMS prop optimization algorithm. RMS prop is root mean square propagation that addresses the problem of rapidly diminishing learning rates in AdaGrad by using a moving average of squared gradients to normalize the learning rates for each parameter. It is selected for its stability in training deep networks with non-stationary objectives. The next one is CNN with BiLSTM with ADAMAX. This configuration employs ADAMAX as an optimization algorithm in hybrid CNN with BiLSTM model. ADAMAX is a variant of ADAM optimizer that uses infinity norm, which is maximum absolute value of the running average of past gradients. It simplifies the computation of the second order momentum. It uses the conjunction with the CNN and bidirectional LSTM aims to strike a balance between computational efficiency and effective feature learning. The next one is CNN with BiLSTM with SGD, which is stochastic gradient descent. It is a hybrid model using stochastic gradient descent as optimization algorithm that updates the model parameters in the direction of negative gradient of the loss function scaled by the learning rate. SGD is a basic optimizer. It is computationally less intensive and can serve as a baseline. In the combination with CNN and BiLSTM, it allows for straightforward comparison to more sophisticated optimizers. The next one is CNN with BiLSTM with AdaGrad. This configuration incorporates AdaGrad as an optimization algorithm that adapts the learning rates for each parameter based on the historical gradient information, assigning larger learning rates to infrequently occurring parameters. The next one is CNN with BiLSTM with FTRL, which is follow the regularized leader, a hybrid model using FTRL as the optimization algorithm combining online learning with the regularization. FTRL maintains per coordinate learning rate and adapts to varying data distributions. As an extension, we applied an hybrid model to produce a more robust and accurate final prediction. Also, as an extension, we built frontend using Flask framework for user testing with user authentication. We evaluated the project using different performance metrics, which are accuracy, precision, recall, and F1 score. So here we have comparison graphs for all those metrics for the dataset, which is NSL-KDD. This is accuracy comparison graph. Here on x-axis, we have accuracy score for each algorithm, and on y-axis, we have algorithm names. Accuracy is a measure of the overall correctness of the model. It calculates the ratio of correctly predicted instances to the total number of instances. This is precision score comparison graph. Here on x-axis, we have precision score for each algorithm, and on y-axis, we have algorithm names. Precision is the ratio of correctly predicted positive observations to the total predicted positives. It evaluates the accuracy of the positive predictions. This is recall comparison graph. Recall measures the ability of the model to capture all relevant instances. It is the ratio of correctly predicted positive observations to the total actual positives. Here we have F1 score comparison graph. It is the harmonic mean of the precision and recall. It provides a balance between precision and recall, especially when there is an imbalance in class distribution. The algorithm which performs well among all these metrics will be used for final prediction. Here we have comparison graphs for UNSW NB15 dataset. This is the code folder of the project. Here we have data in which we will have NSL-KDD and UNSW dataset. We use those datasets for training the algorithms. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is the app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. Here we have two model files which contain algorithm information and that will be loaded into the project code during runtime. Here we have IPYNB files, which are two IPYNB files, and those are the Jupyter Notebook files which contain a combination of codes, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. Here we have signup file, which is the DB file. This file is the database file used to store the user information. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folders path. And here we need to type the command python space app.py and click on enter. This will compile app.py file and it will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which will be the local host and the port unless configured differently. So this is the local host and this is the port. And now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser. And this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on that and enter all the sign up details if you are signing up newly. I have already signed up and I have an account in it, so I will directly sign in. For that we need to click on sign in. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password. And now we need to click on login. We have logged in successfully. And we are redirected to prediction page. Here we can see the parameters which are need to be entered. Based on the given parameters, we will get the prediction whether attack is detected or not. Before entering the parameters, we will understand all the parameters. Here we have protocol type. It indicates the communication protocol used in the network traffic. Here we have service. It specifies the network service or the application associated with the traffic. Here we have source bytes, which are the SRC bytes. It is the number of bytes sent by the source in a network communication. Here we have DST bytes, which are destination bytes. They are the number of bytes received by the destination in a network communication. Here we have logged in. It indicates whether a user is logged in into a service or the system. Here we have count. It is the total number of occurrences or the instances of a specific event or the condition. Here we have SRV count. It is the count of connections to a specific service or the application. Here we have SRV different host rate. It is the rate at which different hosts connects to the same service. Here we have different host count. It is the count of different hosts involved in the communication. Here we have destination host SRV count. It is the count of connections to a specific service on a destination host. Here we have destination host same SRV rate. It is the rate at which destination host connects to the same service. Here we have destination host different SRV rate. It is the rate at which different destination host connects to the different services. Here we have destination host same SRC port rate. It is the rate at which destination host connects using the same source port. Here we have destination host SRV different host rate. It is the rate at which destination host connects to the different hosts for a specific service. Now we have understood all the parameters, so we will enter them. So the protocol type is 1, service is 22, SRC bytes are minus 0.002, destination bytes are minus 0.138, logged in value is 2.396, count is minus 1.5214, SRV count is minus 1.1566. The next value, which is SRV different host rate, is minus 0.2036. Different host rate is minus 3.451. Destination host SRV count is minus 1.694. The next value, which is destination host same SRV rate, is 0.599. Destination host different SRV rate is minus 0.2827. Destination host same SRC port rate is minus 1.02208. The next value, which is destination host SRV different host rate, is minus 0.15863. Now we have entered all the parameters, so we will click on predict. Here we got the prediction as there is no attack detected and it is normal. Now we will enter the parameters again but with the different values and get the prediction. So click on home. I entered all the parameters. Now we will click on predict. So here, based on the given parameters, we got the prediction as there is an attack detected and the attack type is DDoS or probe or R2L or U2R. In this way, If we enter the parameters which are required, we will get the prediction whether attack is detected or not. Now click on sign out. Conclusion of the project. The exploration of various neural network architectures and optimization algorithms reveal that the CNN with BiLSTM model coupled with the carefully selected optimizers stands out as the most effective solution for intrusion detection in network traffic data. Comprehensive evaluation metrics, including accuracy, precision, recall, and FN score, not only validated the robustness of the chosen model but also demonstrated its capability to strike a balance between accurate anomaly detection and minimizing false positives. The project underscores the sensitivity of the model's performance to hyperparameters and emphasizes the significance of thoughtful tuning. Beyond algorithmic choices, the conceptual considerations of the hyperparameter selection, including architecture design and learning rates, play a pivotal role in achieving optimal intrusion detection outcomes. The project's findings carry profound implications for real world network security. The successful application of deep learning architectures in anomaly detection demonstrates the potential to enhance the resilience of computer networks against evolving threats. The conceptual understanding of hyperparameter tuning and model architecture contributes to a more holistic approach to intrusion detection system design. This work opens avenues for further research and implementation in the realm of cybersecurity, emphasizing the practical significance of the project's outcomes.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.